We good? Okay, so my name's Alex Baldwin. I'm a postdoctoral fellow working for Robert Hess in McGill Vision Research. And I'll be talking about some work that I started in my PhD thesis a few years ago and that I still sort of carry on doing from time to time now. So to start with, you probably already know, so the eye works in kind of a similar way to a camera. So light bounces off objects in the outside world, in this case a dog. It gets focused by the lens in the eye onto the back, and then you have photoreceptors there that transform that into electrical energy. So you can compare it to like a digital camera. So on the left of this slide, we have how a digital camera might see this when it divides up the input image into pixels. And then you would say, how good is your camera by the number of megapixels that it has. And then on on your left of this slide, we have a photoreceptor mosaic. So this is what the retina looks like on the back of the eye of some little fish. So the interesting thing about the visual system in the brain is that for a camera, once you've split things up into their pixels and saved them to the memory, you're pretty much done. Whereas for the brain, this is only the very start of the process. You see, it would be easy to imagine that we had a situation like this. So this is our sort of Cartesian theatre thought experiment where you have a little pilot inside your brain, a bit like in the original Men in Black movie. So you have a little guy in there, and then the point of the visual system is just that we're going to project what's happening in the outside world onto that little screen, and then there's somebody inside who pulls the levers, works the arms and the legs and everything. But of course, it's kind of intuitive to feel like you're sort of driving your body around and receiving information from the outside world. But it's not a satisfactory explanation. In order to have a little guy, he has to have a little guy also inside his head, and so on and so forth. So I'm sorry to tell you that that's not how it works. And so it's actually the brain itself that has to do all the processing on the input and then, turn that into behavior. So some of my research concerns how those little sort of local signals that we were getting from the retina in the second slide are then built up into representations. Because you see, vision is it's an active process. It involves most of the brain, and different parts of the brain are specialized for different things. And it's pretty much all about taking that input and then reconstructing it in sort of partial ways. So reconstructing part of it into, this looks like, the face of a dog. Or this was this texture, this was that color, this was, a frisbee, it was moving, it had this trajectory. Different parts of the brain do all of these different sorts of things. And then I look at how these representations are built up in particular areas that I'm interested in using psychophysics, which compared to the other methodologies on display here is very basic. So what I mostly do is I have my humans, who I usually have to pay, sit in front of a computer, and then they're being shown pictures, and they have to make decisions on the basis of those pictures. And then we very carefully design our pictures so that they're testing something very simple, and then we give them very simple tasks to do so that we can easily relate the stimuli they're seeing and the task, and then how they're behaving in response. And then we try and come up with sort of mathematical laws that take us from what people are seeing and the decisions they're making on the basis of that to their behavior. So this is where the sort of psychophysics things come from. So if you imagine in the 19th century, there were some German people who were like, physics is cool, we can use mathematical laws to describe how things work in the outside world, but can we then take that and apply it to, sensations, perceptions? How, in the 1950s, 1940s, there were people writing things about how can we, take the beauty of a piece of art and reduce it to a number, and then say this art is this much beautiful and this art is this much beautiful. That's less in vogue now. It's much more, and just making things be by mathematical laws is less in vogue. Now we're really interested in making it be an explanation of how it is that the brain is doing this processing. So here's a kind of a simple example. So this is one of the lowest levels at which you can look at this. So we have in the top row, we have a small texture, and in the bottom row, we have a bigger texture, just the same thing, repeated. And then as we go from your left to your right, the contrast is decreasing, so it's becoming less visible, it's getting more faint. And then in general, the bigger something is, the easier it is to see. So you should be able to see, it probably doesn't work very well on this screen, but in general, you can see the bottom larger stimulus, when it's more faint, then you could see the top stimulus just because you have more of it. But the particular relationship between how big is it and how visible it is actually depends critically on the exact mathematical processes that are happening inside the brain. And so if we sort of measure how people do on that, so we have size along the bottom here, and then contrast required to see it along the left side, and then all these little like circles or crosses or squares are how visible things are as a function of their size. And then the sort of lines that are going through them are predictions from a mathematical model that has different stages. It has representations of that first stage where we took things in the retina and then various combinations between them. But the point is that we test a whole bunch of different ways things can be connected together, and we find the one that explains how people behave. And then if it's also, that's based on sort of plausible physiology, we say this is probably how it works in the human brain, and until we get a better explanation. So that's basically what I do. I find it a lot of fun because it's all about sort of trying to solve how the brain might solve a problem, and hopefully we can find some way of making it interesting to other people too. So thank you very much.
Thank you, Alex.